Okay, in this lesson we have 2.5, multiplying and dividing imaginary and complex numbers. Now we have two learning goals: to multiply and divide imaginary and complex numbers, and to use the complex conjugate to rationalize the denominator. Okay, so in this lesson we're really just going to be diving right into it. We've already added and subtracted with imaginary and complex numbers, and we're just adding on operations, okay? So let's look at this first example. -4 times 13 plus 5i. You do this the same exact way you always would, okay? Distributive property, right into both. -4 times 13, you get -52. -4 times 5i, you get minus 20i, and that would be it, okay? Now, this next one is what brings us back to FOIL, right? We have a binomial times a binomial. We need to make sure we multiply everything, just like we would if those i's were x's, and that's kind of how you should treat them, okay? You should treat them like they're, any old variable until you get to having an I squared, an I cubed, and you have to deal with it. So let's look at this. We'll go 1 times 2, 1 times 5i, right? Which I'm going to write that out. 1 times 2 plus 5i. And then we have -3 times 2 and -3 times 5i. So I'm going to write that out. All right, now this is what I wrote out is exactly what we're doing, okay? We're taking each term from the first binomial and multiplying it to the second one. I just want you to see the multiplication right now, okay? So here we get 2 plus 10i, 2 plus 5i, and then -3i times 2 is minus 6i, and then -3i times 5i is going to give you minus 15i squared, okay? Now this is where you can't just think of it as a variable anymore, because I squared can be reduced. The only one that we leave as is just I, because we don't want to write the square root of -1, okay? But for the rest of them, for I squared, I cubed, I to the power 4, we are going to make that change, okay? So let's simplify what we can. We have 5i minus 6i, which will give us -i. So 2 plus, let's just write it as 2 minus i. Now we have -15 I squared. Now I squared is the same thing as -1, so that's really -15 times -1, which makes us 2 minus I plus 15, which makes this, let's just go -I plus 17. Okay? Now, that was a lot more steps than the first one. Okay? Let me bring these both back into view. The first one was just a single distribution. The second one we had to distribute twice, and we ended up with an I times an I, so we got an I squared that we had to deal with. This is how multiplying imaginary and complex numbers works. It's 95% what you've already done, and then it's 5%, oh, I have an I squared, let me deal with that, okay? You should only end up with I's, okay? All right, so that was 2. So here I have one for you guys to do. I accidentally left in a division one. Here's a multiplying one. So why don't you guys give 5 times 3 minus 2i a try, and then I'll go over it. Okay, so hopefully you gave that a try. What you want to do is not use an eraser. You want to distribute. You should get 15 minus 10i, okay? Nice and easy and straightforward. All right, let's jump into a math talk, okay? And the reason why we're going to do a math talk is because we have to talk about complex conjugates in order to do dividing of complex numbers. So complex conjugate, which you can see down here in the bottom right, is for a complex number a plus bi. The complex conjugate is a minus bi. And so what you can see is a simple change of operation, okay? And I have some problems up here to kind of prove why the complex conjugate is so important and to demonstrate it. So this first example, 1/4 plus 1/2. You can see that obviously in the past you get this problem. You cannot just add these together. right? They don't have the same denominator. And so what you've always done is you've changed the, one of them or both of them to have the same denominator. And what you've done is you've always multiplied by 1. Now, I know you see it multiplied by 2 over 2, but 2 over 2 is 1, okay? And what that does is it gives you something like this so that you can take another step. Now, 1/2 and 2/4 are the same value. And this like example here to me is the most powerful concept in algebra, is multiplying something by 1. And I don't mean the actual one, I mean 1 equivalence, right? Think about how powerful of a tool this has been. We have fractions that we don't want to add or that we can't add together as is. So let's multiply one of them by 1 to change it so we can. That's powerful skill. And you start to think to yourself, well, are there other places I can use this multiply by 1? And there are. Here, when you have 1 over the square root of 2, okay? The square root of 2 is an irrational number, meaning it's 1 point something, 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 forever, okay? And there are a ton of irrational numbers, all right? And if you have this irrational number that goes on for infinity, how can you have 1 over infinity, right? Or 1 over 1 point infinity? It just doesn't make sense. We like our bottom denominators to make sense. Just kind of like you wouldn't really want to write 3 over -2. How can you have 3 items out of a -2 total? I mean, mathematically, it's the same, we can figure it out, but it just doesn't make sense. We don't like to leave the negative in the denominator, just like we don't like to leave a square root or cube root or any type of root in the denominator. So here, that's where the term rationalizing the denominator comes in. We would multiply by the square root of 2 over the square root of 2, which again is really just 1, okay? So now we get 1 times the square root of 2 up top, which is the square root of 2. And then the square root of 2 times the square root of 2 gives you the square root of 4, which really is just 2. Now I know it looks like we just moved the irrational part above, which we did, but now our denominator makes sense. We have a total of 2 that we could have, okay? So, you probably have seen these first 2 examples. How does this work into imaginary numbers? Well, here, in the first 2, it was very clear, at least, you've learned in the past how to do these, but it's kind of clear when you look at this rationalizing the denominator in the bottom here, that the square root of 2 over the square root of 2 makes sense, okay? If I multiply the square root of 2 by the square root of 2, I get rid of the radical. Well, with an imaginary number in the denominator's place, that again brings us to a situation that does not make sense, right? I have this thing that's not real in my total, and I need to get rid of it. How do I get rid of it? The complex conjugate. You need to multiply by 1, but really you need to multiply by the opposite version, like this. You need to multiply by the complex conjugate in order to get rid of I. Now, when you do this, you end up multiplying, okay? And you've probably seen these examples in the past where you have the same exact binomial where one has a negative and one has a positive, and it ends up canceling out a lot of terms so that we can get rid of I, okay? And I'm going to show that on the next slide, but I just wanted to talk about, again, we're multiplying by 1. I wanted to bring that full circle for you guys. Multiplying by 1 is super, super powerful, okay? Now, let's look at an example. Okay, here we have 25 plus 19i divided by 5 minus 3i. We are going to multiply by 1, but we're going to use the complex conjugate. So we're going to go 5 plus 3i over 5 plus 3i. Notice how the 5's polarity didn't change. Just the imaginary number part changed, okay? And now this brings us back to the first part, multiplying of complex numbers, right? The top is 25 plus 19i times 5 plus 3i. And then the bottom is 5 minus 3i times 5 plus 3i, like that. And so we're really bringing in the multiplying. We're going to do it twice. So we do the top part. 25 times 5 gives you 125. 25 times 3i gives you 75i. 19 times 5, what is that, 95? So 95i. And then 19 times 3i is going to give you, what, 57i. Okay, squared. 57i squared. Don't forget that squared part. That's very important. Okay? And all of this will be over 5 times, let's see, we're going to do 5 times 5, 5 times 3i, negative 3i times 5, negative 3i times 3i. And we get 25 plus 15i minus 15i minus 9i squared. Okay? Now this middle part here, this 15i minus 15i, that is because we multiplied by the complex conjugate. That is what we achieved by multiplying by the same exact binomial, but with a plus instead of a minus. Okay? 15i minus 15i cancels, and you end up with 0. Now you think to yourself, well, the whole point is to get rid of the imaginary number on the bottom, but I still have an imaginary number on the bottom, but we have an I squared. And I squared is also negative 1. And we can do that on the top and the bottom. So our new part here is 125, and I'm going to start to simplify. 75i plus 95i is 170i. And now it's actually not plus 57 anymore, because that's 57 times negative 1. So it's just minus 57. Okay? And then over 25, and now it's not minus 9i squared, because that's a negative 1, and negative times negative is positive. That's just plus 9. Now we can do some further simplifying here, right? On the top, we can have 125 minus 57. And on the bottom, we can have 25 plus 9, okay? And so minus 57 is going to bring us to 68. Yeah, that's right. Plus 170i over 25 plus 9 is 36. Okay, and now we have rationalized the denominator. Okay, and think about that word, rationalizing it. We've given it a rational number of 36 instead of a complex number or an irrational number. Okay, and that would be the end of this problem. All right, now I have another one to do. 8 plus 19i divided by 4 plus 3i. And the reason why I'm doing this one is because I want you to see how we do a complex conjugate when there's a plus instead of a minus. And it's the same thing. You just do the opposite. This becomes, multiplying by 4 minus 3i over 4 minus 3i. Okay, the opposite is the complex conjugate. And then it's everything you've been doing, right? This is 8 plus 19i times 4 minus 3i over 4 plus 3i times 4 minus 3i. Okay? And then we go through 8 times 4, 8 times negative 3, 19i times 4, 19i times negative 3. And we're going to get, let's see, 32 minus 24i plus, 40, 36, 76i minus, man, a lot of bigger stuff today, 57i squared. Okay. Over 16 minus 12i plus 12i minus 9i squared. And again, you can see we get this canceling out in the middle. That should let you know that you did the complex conjugate correctly, okay? Or at least mostly correctly. Now on the top, we still have a lot to deal with here, right? We have, okay, negative 57i squared, which that's really just going to be a positive 57 now. And so we have 32 over here, and that 57, we're going to combine those in a second. We have negative 24i plus 72. That should bring us to positive 52i, okay? And then let's just do that top part. 32 plus 57, you should get, what, 89? Yeah, 89 plus 52i. All of this will be over. We still have that 16, and then it's right here, negative 9i squared, which that I squared is a negative 1, so it becomes a plus 9. and we end up with 89 plus 52i over 25, like that, okay? Now, again, we have given a real number to the denominator. That is the goal of the complex conjugate. It's okay that there's still an imaginary number up top. Sometimes you can't fully get rid of them, all right? Now I have one for you guys to do, negative 32 plus 8i divided by 5 plus 3i. Give it a try, and then I'll go over it. Okay, so a couple things, all right? This first thing we need to do is find the complex conjugate. It's the opposite. It's 5 minus 3i over 5 minus 3i. Okay, once we do that, we go right into multiplying. We have negative 32 plus 8i times 5 minus 3i over 5 plus 3i times 5 minus 3i. Okay, and we're going to jump right into it. So negative 32 times 5 gives you negative 160 plus 96i. That's negative 32. So let me draw those out. We did negative 32 times 5, negative 32 times negative 3i. And then we'll do 8i times 5, which is 40i. And then we're going to do 8i times negative 3i, which is minus 24i squared. Okay, all of this will be over 5 times 5 and 5 times negative 3i. That gives you 25 minus 15i. 3i times 5, 3i times negative 3i gives you plus 15i minus 9i squared. Okay, seeing a lot of minus 9i squareds tonight. That's a coincidence. You should start to see other numbers there in your assignment. So we go and simplify. I'm going to simplify these squareds first and get them out of the way. That should be, I'm going to write them up there, okay? We should have a positive 24 now and a positive 9 now, okay? I did that right on the last page, right? Sweet. Did I? Yeah, I did. Okay, awesome. All right, so we have 24 and 9 instead because of that I squared. And I'm going to go right into simplifying. Negative 60 plus 24 is negative 136. 96i plus 40i gives you 136i. And all of this should be over because those negatives cancel. 25 plus 9, which is 36. Okay. All right. And that should have been your final answer. Let me just quickly check that. Yep. Good. Good. Okay. And that should have been your final answer. All right. Now I have a couple what if sections. All right. In our multiplying, we did, a single distribution and a double distribution, but we kept everything at the I squared level. All right. It's not unheard of to see maybe something like this, I to the power of 3 times 2, plus I or something like that, right? It's the same thing, treated as a variable. If you multiplied in, you would get 2I cubed plus I to the power of 4, which then now, because we have higher stuff than just I, we would simplify that. I cubed is the same thing as negative I, so that's 2 times negative I. I to the power of 4 is the same thing as 1, so this would really just be negative 2I plus 1. Now you shouldn't see too much of this caliber, but I wanted you to see, what if I had other types of i's? You would do the same exact thing you've always done. Multiply them, and then, just increase your exponents appropriately. I to the power of 3 times I is I to the power of 4. Now, with division, you saw a lot of examples that had the full complex number on the bottom. And what I mean by that is you had the full a plus bi. Okay, you have like a 3 plus 2i, a 3 minus 2i, all that kind of stuff. Okay, but what if I had, let's do 12 plus 3i divided by 2i, and there was just a single term. what would you do to find the complex conjugate? And this would actually just be easier. You have a positive 2i, so you would multiply by negative 2i over negative 2i, and that would be it, okay? This would basically be the same thing as 0 plus 2i, and so you're still flipping the same exact sign that you always would. There's just a single term, okay? So hopefully that kind of clears up a little bit about multiplying and dividing complex numbers, and I hope you guys understood it. Okay, I'll talk to you next time.